All right, let's go ahead and get started. So we're going to finish up section 3.3, and we'll start 3.5. We'll skip over 3.4. We'll start 3.5 after that. So look at this function here. So for a big chunk of what we did on Wednesday, we were dealing with derivatives of log functions. Now we're going to look at the derivative of an exponential function. So we could go back to the difference quotient limit here, but let's go a different way. So I'm going to call this function y equals a to the x. We know that logs and exponential functions are inverses of one another. So let's go ahead and rewrite this thing. How can I rewrite this thing as a log equation?
Log base ax.
That would work. Let's do a natural log of both sides. Well, I'm gonna take a natural log of both sides and see where we end up. So I have natural log of y equals the natural log of a to the x. So this gives me, so natural log of y. What can I do to this right-hand side? Can I rewrite that in a special way?
X natural log of a.
So yeah, x times the natural log of a. So now I have the whole point of me, I don't know how to deal with things where I have the exponent in the, the exponent is the variable. So let's get out of that situation. Now, can I take a derivative of both sides with respect to x? So let's do that. Start with the right-hand side first. What's the derivative of x natural log of a with respect to x? What is true about the natural log of a? What kind of thing is that? Is it variable? Is it constant?
A is constant.
A is a constant, so is natural log of a constant? That's basically, it's like a linear thing over there. You have some constant times x, so the derivative of that is just, well, it's the constant. What's the derivative of 5x? 5. So same kind of thing here. You have a constant times x, the derivative is whatever the constant is. All right, so what's the derivative of a natural log of y, but with respect to x? So you have x going through some function that transforms it into y, then it goes through some other function which transforms it into natural log of y. What's the derivative of the natural log function? We talked about that for quite a while on Wednesday. 1 over y. So the derivative of natural log of y with respect to y is 1 over y. The derivative of y with respect to x is, that's the thing we're really going after, right? We want to find dy dx. So we got this, dy dx equals y times the natural log of a, which is equal to a to the x times the natural log of a. Any question about how we put that together?
Yeah, how?
How what? Where did I lose you? What is y equal to?
X.
Which is equal to? A to the x, right? So yeah, I mean, this is, if you think back to that long, nasty log differentiation we did,
we did the same thing.
Yeah, so basically, you're gonna get to a place where you have dy dx equals something in terms of y and x, but you knew what y was at the outset, so you just redefine it.
On the fourth line, could you explain again how we got natural log of 3 on the right side?
Sure, so this right here, are you okay with the idea that the natural log of a is a constant? So I'm going to say this, let's say k equals the natural log of a. Then what I'm really doing is take the derivative with respect to x of kx, which is, that's just a constant times x, right? We can think of that as power rule, but that comes out to k times the derivative of x, which is equal to k times 1. So basically, if I were to graph out x natural log of a, it would be a straight line that cuts to the origin at a slope of what? Of natural log of a. So that's why the x falls away. It's linear, even though it's strange looking, it's linear. Anything else here? All right, so here's the new rule we gave you and the consequence of it. What's the derivative of e to the x? Well, if I follow that rule above, it should be what?
EX,
Yeah, so e to the x times the natural log of e. What's the natural log of e?
1.
So e to the x. And this is another reason that when we're doing exponential functions, especially in terms of calculus, we really love to use e to the x because it is its own derivative. How we doing? Okay. All right. So let's use this thing. I want to differentiate f of x equals 3 to the x to the 5. How should we approach this? How should we think about it?
Have to do a natural log just to get the variable down.
No, we don't. Not anymore. We have a way to avoid that. So I'll say this: we absolutely could do that. I'm gonna go ahead and say no because I'm trying to. We just learned how to do derivatives of exponential functions. Let's use that. So we want to use the rule we just looked at. Are there any other things we need to bring in?
We have to use the power rule after we use the differentiation rule.
Why do you think that?
Because if you use the differentiation rule, it would look like 3 dx to the 5 times ln 3.
3 to the x to the 5 times the natural log of 3. Is that all that? Okay, let's think about this. Here's my block diagram. What's the first thing that happens to our input x?
Gets raise the power of 5.
Gets raised to the power of 5, right? So x to the 5th. What happens to x to the 5th? This is a hard thing to think about.
It is the power of 3.
Yeah, it gets 3 raised to it, right? Which is a weird thing to think of, but that is what's happening. So first I raise x to the power of 5, then that thing becomes the power to which 3 is raised. So and then what comes out is 3 to the x to the 5th. So the way I wrote those functions out, that's all one series, right? Kind of like a chain. So And that's the reason I keep drawing these things out, because if you can get that series of steps, this series of simpler functions, that's a composed function. That's what the chain rule was developed for. So now that we have these two functions, let's write them out. We'll call this one G, we'll call this one H, which means f of x is equal to h of g or g of h?
H of G.
H of g of x. Now let's define these things. What is g of x?
X to the 5.
X to the fifth? Yeah, x comes in, x to the fifth comes out. What is h of x?
3 to the X to the 5th.
Not quite 3 to the x to the fifth.
3 to the X.
Is 3 to the x, because, yeah, what came into that right-hand block was x to the fifth. What came out, I didn't modify the power on x. I just took that thing and made it the power that I'm raising 3 to. So these are my two functions. What's the derivative of g? 5x to the fourth. What's the derivative of h? This is the brand new one.
3x times ln 3.
3x times the natural log of 3. So if I'm going to set it up, if I'm going to take this derivative using the chain rule, I'm going to take the derivative of h, but I'm going to keep the input g intact, so that becomes 3 to the x to the fifth natural log of 3, which is what we said earlier, right? Do we still think that's okay? Are we done?
No, there's more with that.
Right.
First part.
The first part, yeah, so it doesn't contains we had the derivative of the outer function done. We just need to take the derivative of the inner function, which is 5x to the fourth. How does this thing simplify? It doesn't really. I'm just going to write it in the order that I like. Any questions there? We understand why chain rules involved there. Okay. Anything else? All right. Y equals cosine e to the x. I want to find, what do I want to find here? Yeah, y double prime. So how do I have to start? So what tells you got to do chain rule?
So E is being raised to power x, and then whatever that input is going to cosine.
Right. So I mean, the way you're describing what this function does, it's, you know, a series of steps. First, x becomes the power on e. Then that object has the cosine taken of it, right? All right. So what is the derivative of the cosine function?
Negative sign.
So this becomes negative sine of x.
No.
Remember, for chain rule, we have to respect whatever the input was to,
Negative sign e to the x.
yeah, negative sine of e to the x is the first bit there. Then I need the derivative of the other function. So what's the derivative of, or I'll ask this first, what is the inner function? E to the power of x. What's the derivative of e to the power of x?
Yes.
E to the x. So our first derivative is negative e to the x sine e to the x.
Is it negative e because the sign is negative?
Yeah, I'm just moving things around. Which technically you don't have to do. I have personal preferences about where things. Yeah, we're not wrong after the first step there. for some reason, it hurts my eyes to not have e to the x first. So now what do we got to do?
I'm moving over that.
Take that derivative again. So we're gonna go y double prime. We had to use chain rule the first time, we have to use it again.
Yep.
Anything else we got to think about?
Product rule.
Product rule, yes. So those two things for sure, right? So how does product rule work? What do we got to do?
We define functions g with h.
Okay, so let's not do this yet. Let's figure out g of x times h of x. What's g of x?
Yes.
No, sine, negative sine e to x.
Negative e to x.
Okay, I mean, really, you could do negative sine of x and e to the x, but let's keep these things together. So then what's g prime of x?
Negative c x.
Yep. What is h prime of x?
That's where we need.
Yeah, we need chain rule, but we we didn't really pull it apart slowly. So can we try to do it quickly again? So we had the series of steps last time, right? That Solomon laid out for us. In sine of e to the x, what's the first thing that happens to x?
It gets applied to like as the power.
Right, it's hard to say, right? So yeah, it gets
Sine.
it gets exponentiated. I'll try that one. It gets exponentiated by e. After that happens, then what happens?
Then it gets multiplied by sine.
Not multiplied by sine, but take the sine of it.
Oh,
Yeah, it's not a multiplication, even though they're next to each other. So that's the series of steps, right? So the first thing I got to ask is what's the derivative of what function? What is the outer function in this case?
oh, just cos negative. Is it negative?
It's just cosine.
Cosine.
So cosine of what though? E to the x. Is that it?
Sine times negative x.
Just e to the x. Keep in mind what h is. H is all positive. Yeah, nothing is going to make the negative crop up there. All right, so now I think we have enough. So what is, I'm going to start a new down here. What is y double prime?
Negative e to the x times sine e to the x.
All right, there's one term.
Plus negative e to the x cosine ex times e to the x.
Negative e to the x cosine e to the x times e to the x, right?
Mhm.
I can clean that up a little bit. What is e to the x times e to the x?
One.
No. Think about your exponent rules. They have the same base, right? What do you do to the exponents when you have the same base and you're multiplying?
Add together.
Right, so that would become
E to the 2x.
e to the 2x. E to the 2x cosine e to the x. Any questions? All right. All right, f of x equals the natural log of 3e to the 5. What's f prime of x? What do we need to look at?
Product rule that we just learned as well.
So product rules. So f of x equals G of x times h of x. What's g of x? Okay. What's h of x? What is g prime?
Derivative of a constant.
What's h prime of x? So what's the derivative of the whole thing? So you told me natural log of 3 is a constant?
Yeah.
And e to the 5th is a constant?
Yeah.
So what happens if I multiply those things together? It's a constant, right? So what's the derivative?
0.
Oh, yeah.
It's not solid.
Yeah, well, you saw it. And that's, I mean, that's why I threw that in there, because it's like, oh, I got a thing raised to a power rule. Make sure it's actually a variable. Just like in, I think when we were going through the proof of what the derivative of the x was. It took all of us a while to see that x natural log of a was x times a constant. So just pointing out that keep an eye on what the variables are. Locate those. If they're not there, then yeah, this is a very simple matter. Any questions there? All right, I think that is it for 3.3. On to 3.5.
What's 3, 4?
I don't remember what 3.4 is. But what's that?
What's the power?
Oh, yeah. Inverse trigonometric functions. So we skipped 3.4 and 3.6. One of them is about something called Newton's method, which is worth skipping. We'll say it politely. I can't remember what 3.4 is, but I'm pretty sure 3.6 is Newton method. All right, so what kinds of functions have inverses?
One-to-one.
Only one-to-one functions, right? So is sine of x 1-to-1?
Yes.
No,
Oh, I've heard yes and no.
the sine or cosine can't be 1-to-1 because they don't have the horizontal.
Yeah, horizontal line. So I mean, sine and cosine are periodic, right? So it means for every y value, there's infinitely many x values that give you that y value, right? Is tangent the same way? So sine and cosine both look like this, right? If I don't put them on a set of axes, they both have that shape. Tangent kind of looks like this. I mean, it has these curves that appear at regular intervals that are all the same shape. So is that one 1-to-1?
Visually, those lines are.
Those are all one graph.
I won't say no.
Yeah.
Oh,
No, so yeah, I wasn't graphing tangent several times. If you graph tangent, an infinite number of those appear side by side.
One test is horizontal.
So let's think about that. So 1-to-1 means that for every y value,
One corresponding.
there's one corresponding x, right? So what's going to tell you that, a horizontal line or a vertical line? A horizontal line.
And then versus
Vertical. What does the vertical line test tell you?
just a function.
If it's just a function at all. If it fails that, it's not even a function, and you don't have to think about 1-to-1. But we deal in functions. So none of those things are 1-to-1, which means none of them have inverses. But all of your calculators have inverse, sine, cosine, and tangent buttons. So They have to make some kind of sense, right? So let's look at a graph of the sine function. They're periodic, so let's call this one 1. So they just repeat over and over again. And I think on the homework, which was due last night, you had to deal with the inverse of a quadratic, right? I think that was one of those problems on there. Are quadratics 1-to-1? No. Parabolas are never 1-to-1. So how did I ask you to deal with the inverse of a parabola? Something you're allowed to do is you can restrict the domain. So this thing is not 1-to-1, but I can cut down, basically I can delete x values until it is. So that's why I can force a function that has no inverse into having an inverse. So what is the range of the sine function? I think I heard -1-to-1. So it goes as low as -1, as high as 1, right? So here's what I want to, when I restrict it, I want to keep that full range. I just don't want to hit any of those range values more than once. So how can I cut this down? Like this. So now I still have a function that has the full range of values from -1-to-1. Is that 1-to-1? Cool. So what did I restrict the domain to?
-pi/2.
Including those points?
Yes.
Yeah, I can include. So this is how, when we deal with things like inverse sine, inverse cosine, inverse tangent, you are by definition restricting the domain. So if you take the inverse sine of like 0.2 or -0.2 or anything inside this domain, because they flip, you better get something inside this range. And if you notice, when you take the inverse sine of something, you always get something in the first quadrant or the fourth quadrant, because that's how these functions are defined. So moving on to cosine then. Don't need a good sketch, just a good enough one. So what's the range of this function?
-1-to-1.
Still -1-to-1, good. Clearly not 1-to-1, right? So how can I restrict this one to make it 1-to-1?
0 to pi.
0 to pi. Is that 1-to-1? Does it contain all the y values that I want?
Yeah.
Good. So this is 0 to pi. And just like for inverse sine, if you take the inverse cosine, you will always get something in the first quadrant or the second. And then tangent looks quite a bit different from both of those. This is the one that, has a bunch of these curves that appear at regular intervals. What's the range of this function? Yeah, all real numbers, right? So the range is from -∞ to infinity. How do I restrict this domain to make it 1-to-1? Right, this one may be a little more clear because I can just keep the one of those that passes through the origin. So this is -pi/2 to pi/2. Do I include -pi/2 and pi/2? Why not? Yeah, tangent is not even defined there, which means it's not continuous there. So this is how I restrict the domain of tangent, so I can even talk about its inverse. So any questions on any of these? Okay. So let's use these. I want to find the arctangent or inverse tangent of radical 3 exactly. So let's do this first. Let's give it a name. Let's say y is equal to arctangent of radical 3. Can I use some kind of a inverse function relationship to give some other information here? If y is equal to arctangent of negative or radical 3, then can I say this? Can I say tangent of something equals something else? How do I fill in those blanks? Tangent of y is equal to radical 3. And one thing I'll show you here is if y is equal to the arctangent of radical 3, I can take the tangent of both sides, right? Tangent of y equals the tangent of the arctangent radical 3. What happens when you compose a function with its inverse, like I have on the right-hand side? They cancel, right? So, I mean, if you think about, I don't know if I've used this language in this class, but one thing that happens when so a function and its inverse will undo one another. So if I send radical 3 to the inverse tangent, and then I send it to the inverse of that, the inverse of the inverse tangent, I better just get what I started with, which is radical 3. So this is good. We have the tangent of y equals radical 3. We're dealing with inverses, so we're in this realm now where we've restricted the domain down to, the domain is no longer infinitely, or it's been restricted to only like a small interval. So what kind of things can y be? What did we say the domain of tangent became?
All real numbers.
No, it can't be all real numbers. The range of tangent is all real numbers. We're talking about the domain though. So y is in between what two things?
Negative pi halves and pi halves.
Negative pi over 2 and pi over 2. So let's draw everyone's favorite thing, the unit circle. If I'm between negative pi over 2 and pi over 2, what part of this unit circle do I not even have to look at? The left-hand side. Because negative pi over 2 is here. This is 0. This is pi over 2. I know my angle is somewhere in between those. I also know that tangent of y is positive. So maybe this is one thing we should review first. Let me draw half a unit circle here. So if I have a unit circle, half of it, if I pick some arbitrary angle, we'll call it theta, that angle projects a point xy onto the circumference of the unit circle. That x coordinate, so that horizontal distance from the origin out to that point, how is that related to that angle? Do you remember that? So that is by definition the cosine of that angle. When you're taking the cosine of the angle, really what you're asking is, when I use that angle to project a point onto the unit circle, what is the horizontal distance of that point from the origin? Or what is its x coordinates? And similarly, y is the vertical distance from the origin to that point. How is tangent related to either one of those things? Go ahead.
To get tangent sine of the cosine.
Right, so the tangent of an angle is equal to sine theta over cosine theta, or in the language of these coordinates, this ratio of y over x. So if sine is the y value, where is the sine of an angle going to be positive? What quadrants? Quadrant 1, anywhere else? Now let's reopen it to all 4 quadrants for this question. So quadrant 1 and where else? The sine? Sine's the y value.
Oh, sorry, I forgot to go backwards, so.
Yeah.
1.
So quadrant 1 and quadrant 2 for the y value. How about cosine, the x value? Where is that going to be positive?
3 and 4. 1 and 1.
1 and 4. Tangent's kind of tricky. So if y over x is positive, what has to be true about y and x?
They both have to agree with something.
Yeah, they just have to agree, right? They don't have to both be positive. They can be. If they're both positive, what quadrant is that?
1.
Or they could also both be negative. That's 3. So we know that for the tangent to be positive, I could be in either quadrant 1 or 3, right? I'm not even looking at 3 to begin with. So here's what I know. I know this angle that I'm looking for is going to be between 0 and pi over 2. Now, how do we find out exactly what it is? Let's pull this triangle out. I called it theta in that generic diagram, but really I'm looking for y, right? Do I know anything about the side length of this triangle? If tangent of y is equal to radical 3,
And what the right side, like right side of that triangle is going to be 3, and the bottom is going to be 1. And there's the Pythagorean too. And then it's gonna be-
yeah.
And then the next one's going to be 2.
So let me back up a couple of steps. How did you know that radical 3 was the height and 1 was the base?
Because the sine it has to be y over x, then the y value, which is the vertical value, has to be 3.
Right. So this triangle here, is it jumping out at you what that angle y has to be? One of those special triangles, what they call the special triangles. So it's going to involve the 30 or 45 or 60. Is that the 40? So is that the 45, 45, 90 triangle? How do you know it's not?
It's not isosceles.
Right. The legs are different lengths. So y must be 30 or 60 degrees, right? Can you say which one of those two it is?
30.
I disagree. Which is bigger, radical 3 or 1?
Oh. 6.
So radical 3 is bigger than 1, right? Which means the angle opposite radical 3 has to be bigger than the angle opposite 1. Which means y is, and we're going to speak in radians. So y equals pi over 3. Go ahead.
You can also do it in the calculator with tan y is equal to radical 3, so y is equal to.
And if you recognize that as pi over 3, that's okay. But if I want this exactly, the calculator is not going to give it to you exactly.
What was it that you called the triangle again? Special triangle?
Yeah, I mean, the special triangles, that was the language I always heard when I was taught these, but these are the triangles that where you can give all their ratios exactly. So there's and basically it's just two triangles, but you know, they can show up in any quadrant. So some of these things might be negative, but basically these side lengths always come in these ratios. So the 45, 45, 90 triangle, these legs have to be the same. Hypotenuse is usually 1. And this other triangle, Not exactly the same as the way we labeled it below, but hopefully you see that they are similar. If I take all the sides on the one I drew up here and double them, I will get the triangle that I made below. But when you're talking about ratios, I don't care about the scale factor. The ratio of radical 3 to 1 is the same as the ratio from radical 3/2 to 1/2. So I know trig is a thing that kind of it's a hard thing to get a hold of. So ask me whatever questions you got about things like this. So yeah, ask me now or ask me later, but a lot of these are going to be on the web work and quizzes and things like that. How about this? What's the cosine of the inverse sine of 5/13? So really should probably look at this one step at a time. So what's the input to this weird thing here, this expression?
Inverse 5/13.
Well, the input is 5/13, right? Yeah. So what's happening to this 5/13 first?
Input into sine inverse.
Yep. So let's try to think about that first. Let's give it a name. Let's say x is equal to the inverse sine of 5/13. Where is, so let me ask this, maybe we should probably talk about this. If I'm taking the inverse sine of something, what kind of object will be the output? What's the right way to say this? Let's do this first. I wrote it this way. Can I use some kind of inverse relationship to write this a different way? Cosecant is not the same thing as inverse sine.
Yes.
No, that's not what I was saying. So I understand why you think that when you see to the power of -1, it is so.
Sine inverse 1 is not the same as reciprocal. So
Yes, that is, so these two things are, I know the notation is confusing because yeah, if it was x to the -1, that's 1/x. That is, so that is a different context in this, and this is one of those math things that if I could go back in time, I would probably do it differently, but this is what we got. So yeah, cosecant is not, I mean, the reciprocal of sine is cosecant, but we don't have to do that here. This is purely in the language of inverse functions. So if x is equal to the inverse sine of 5/13, what's another way I can re-express this by?
Sine x is equal to 5/13.
There you go. So if I'm taking the sine of something, what kind of thing does x have to be? Like what kind of measurement?
An angle.
It has to be an angle, right? So we know that x has to be an angle. And based on what we talked about with sine, do we know anything about where that angle has to be?
Positive sine, so it has to be the first quadrant.
It has to be in the first quadrant. So that's true. But the one thing I want to make sure we have a handle on is I'm taking, x has to be an angle, and I'm taking the sine of that angle. So which means I've restricted the domain. It could be in quadrant 1 or it could be in one other quadrant. Not quadrant 2,
4.
quadrant 4. Yeah, sine is positive in quadrant 1, negative in quadrant 4. So that's how I know it's in quadrant 1. So here's what I know. Actually, I'm going to just avoid this altogether. We know that x is less than pi/2, or equal, I guess. And so it's between 0 and pi/2, right? I guess I should pause there. Are we okay with saying that x is somewhere between 0 and pi/2?
Yeah.
Are we okay with? Follow-up question. Do we understand why I'm just ignoring negative pi over 2 to 0? Okay.
Because
Yeah.
it's possible.
Because because the sign of that angle is positive, I know it's not quadrant 4. Must be in quadrant 1. So this angle x, do I know anything about the side lengths of this triangle?
Yeah.
Can I label any of them?
Yes.
How so?
So you could label the vertical one 5/13.
Call this 5/13. Can I label anything else something? What is the, so when we talk about what the sign, like what the definition of sign is in the language of circles, the unit circle? When you're talking about this triangle context, what's the sign of an angle? Opposite over hypotenuse, right? So I'm going to draw a couple triangles. If this side is 5/13, what does the hypotenuse have to be? 1. Those of you who glared when he said 5/13 is that side, it was more than a couple of you. I'm going to guess you were thinking this triangle.
Yeah.
What is the sign of x in the right-hand triangle? What's the sign of x in the left-hand triangle? 5/13. So when you're doing sine, cosine, tangent, all I care about is the ratios. I could call the right-hand side 5,000 and the hypotenuse 13,000, and we still get to the right place. All right, we okay with that?
So it's the same thing.
Yeah.
Yeah, I mean, you can, I'm going to finish it both ways.
So when you have a sine of x equals a fraction like that, with the denominator always equal to the hypotenuse, and the numerator is.
It can be.
It can be.
That's not what Derek said. But what my point is, the sine, cosine, and tangent of angles is always a ratio, right? I'm going to divide this thing by the other thing. So if that side is 13 times larger, and that other side is also 13 times larger, it's going to wash out. You're going to get the same 5/13 for the sine of this angle. So all that to say that if it makes you feel better, and I think judging by the faces I saw in the room, most people were thinking about this way.
Just because it's easier to look at.
Yeah.
I'm just wondering which number we're on which side.
Oh, that's a good question. So again, in the language of right triangles, what is the sign of an angle? That's how we know. What's the side opposite of the angle? It's the vertical. And the hypotenuse is. Can we find the length of that base? How? Yeah. And because we have 2 minutes, I will fast forward and tell you this is what it is. That comes from Pythagorean theorem. Now that I have these triangles, could we figure out what cosine of the inverse sine of 5/13 is? That's a lot, that's a mouthful, right? Didn't we give a name to the inverse sine of 5/13?
Yes.
What do we call it? Okay, so I guess what I'm really asking you is this. What's the cosine of x? Let's look at Jarek's triangle first. What's the cosine of x on this triangle?
Probably 18 over 12 over 13.
12 over 13, right? What's the cosine on this triangle?
12.
Not 12. Cosine is not just, so what's the cosine of an angle in a triangle? It's not just the adjacent side, the adjacent over hypotenuse. So 12/13. That is it. So I agree. I mean, when I first showed that to you, can I draw a box? When we first showed that to you, it was hard to think about how to handle it all at once, and really, you don't want to. If you take it one step at a time, it's a lot easier to deal with. Not easy, just easier. Note that we never found value in the angles here. I think if you do that, there's no way you're gonna get 12/13 back, because some rounding is gonna have to happen. Any questions here? Okay, probably some review of just basic trick things that are gonna have to come up. If you need help with that stuff, definitely let's talk to each other, talk to me, come to office hours. But obviously that's gonna be a big part of this inverse tree section. All right, oh, I forgot to let you know, I put up the quiz number 6. I made it due the Sunday before spring break because I don't like assigning things over spring break, but if you really want to spend spring break with that thing hanging over your head, I don't care if you turn it in a week after. But right now it's due on the 6th. And I will see you all Monday. Go ahead.
Do we have to memorize this, that when we are given inverse tan, then the angle has to be between -5/2?
It's probably better if you end up remembering it, but keep in mind that how we found this. This comes from the desire to make the tangent function 1-to-1,
Yeah.
which
So that it
the natural way to do that is to,
horizontal line test.
yeah, the natural way to do that is to restrict it to that, to those two, to this interval.
Okay, so for tan inverse one, this is the equation, and for cos, it's 0 to
Mhm.
pi/2.
And that comes from the same thing. Like if you draw the graph, like, let me bring it up.